Hello, everybody. And the title of my presentation is Tensor-Based Regression Models and Applications. And here's the outline. I will start the presentation by introducing the context of our research and motivations. Then I will briefly review the tensor basics which are useful to understand this presentation. And after that, I will give the details of our contribution, which includes 5 separate contributions from different settings of modelings. And finally, I'll conclude this presentation with the summary of the contributions. And regression is a statistical technique that attempts to study the relationship between 2 more variables. It can be used to predict one or more response from a set of predictors, or it can be used to identify the key factors behind observed patterns by exploring the correlation among the variables. And the regression models can typically be categorized into linear and nonlinear regression models. For linear regression, notable examples are simple regression, multivariate regression, generalized linear model, or partial least squares. And for nonlinear regression, examples are Gaussian process, artificial neural networks, and the support vector regression. And however, these classical regression approaches have confronted great challenges posed by the real-life regression task, whose input-output takes form of high-order tensors. Typical examples include using brain images to diagnose neurodegenerative disease or to identify the brain regions that are associated with the clinical results by treating the third-order tensor MIR as the predictor and by treating the scalar clinical outcome as a response. And other examples are to estimate 3D human pose positions from video sequence or to reconstruct the limb movement trajectories from the ECOG signals of monkeys. And however, the primary reason why these classical regression approaches fail to handle this tensor regression task is because those data contain multivariate structure information that cannot be captured by the vector-based regression models. And vectorizing operations will destroy the underlying multivariate structure of the tensor data, and it further suffer from the fact that the ultra-high dimensionality will produce huge amount of parameters, which will lead to an overfitting situation and break the theoretical guarantee of the classical regression approaches. And other drawbacks include such as difficulty of interpretation, sensitive noise, and lack of uniqueness. And for these reasons, my research has been focusing on the tensor-based regression modelings, which are more beneficial since they can naturally preserve the multivariate structure information and in a much more compact format with only a few number of parameters. And with such useful prior information and representation, the predictability can be significantly improved. And other advantage includes ease of interpretation, robust noise, and uniqueness property under some mild conditions. And so what are tensors? Tensors are just high-order generalization of metrics and vectors. They are also refers to multivariate array of real numbers. The order D represent the number of dimensions, and each dimension is called mode array. The number of variables in each mode is used to indicate the dimensionality of that mode. And here is an example of third-order tensor of 3 indices of size I1, I2, and 3, each element of which have 3 indices. And D-mode vector is just called D-mode fibered. It's a high-order analog of the matrix rows columns. It's defined by fixing every index except 1. And D-mode metrization is also known as D-mode unfolding and denoted as XD. And here example of a third-order tensor I1, I2, I3, which is unfolded along the first mode and the second mode, leading to a matrix of X1 of size I1 by I2, I3, and a matrix X2 of size I2 by I1, I3. And D rank is denoted by the rank of rank D of tensor is just the column rank of the unfolding matrix in the D mode. And the collection of D rank is just the multilinear rank. And one of the fundamental tensor decomposition is called CP decomposition. And it is considered to be a high-order generalization of SVD, and it is also considered to be an extension of linear factor model to multilinear data. And mathematically, it can be defined. It can be defined as a linear combination of rank 1 tensors, and here the factor matrix in the D mode is includes all the factor columns. Is just used to summarize the patterns or structures of data from that mode. And the second fundamental decomposition is called Tucker decomposition. Is a form of Helder PCA. And it decomposes a tensor into a co-tensor multiply factor matrix along each mode. And the factor matrix, which are usually orthogonal, can be thought of as principal components along each mode. And entries of the co-tensor is to show the level of interaction between different components. And furthermore, in fact, CP decomposition can be thought of as a special case of Tucker decomposition with this restrict superdiagonal cotensor. And before introducing our main contributions, I'd like to first take a look at them from the very top level. And under the nonlinear assumptions, here's a picture of our contributions. Under the multilinear assumptions, our batch H-Tucker regression is able to handle potentially very high order input. And our sequential IRGPRS is designed for the context of infinite time-dependent tensor streams. And our RHPLS is a general sequential framework, which is especially useful for the large-scale, high-speed tensor sequence. And in the nonlinear setting, our sequential tensor OLGP can be used for the large data sequence in an online fashion, while our KMP-TRS can be used to merging multiple tensor blocks to boost the predictabilities. And here's our first contribution. It's called H-Tucker decomposition. This work is published at ICIP 2015, and this work is targeted on the batch multilinear regression modeling with tensor. This work is motivated by the weakness of CPU regression, which is not flexible because of this restricted superdiagonal cotensor. The lack of flexibility will lead to an underfitting situation and low predictability. And the Tucker regression is flexible but not scalable to very high order tensor because of this exponential growth of parameters with order D. And to this end, we just introduce low-rank generalized linear tensor regression by approximating regression coefficient tensor using a hierarchical Tucker representation. So it can preserve the flexibility like Tucker by allowing distinct rank according to a dimension tree structure. And it also enjoys the advantage of CP-based model in that the number of parameters is free of dimensional dependency on the order D. And it is essentially useful for the brain image data analysis because the only limited number of samples available for most of the data set for brain image data analysis. And here's our modeling strategy is based on the generalized linear model, and with the linear systematic part is like this. And here mu is just the mean of distribution in an exponential family. G is the link function. It is a linear combination of the unknown parameters. Here B is the full coefficient tensor, which has same size as X, captures the effects of each element of X. And here the Z is just the regular vector predictor, B is a regular vector coefficient, and this linear term just incorporates the conventional features into the model, and the B just intercept. And the problem with this model is that the B has the same number of parameters with X, and which is huge. So the natural idea to find a less parameter to approximate B. So based on the advantage of H-Tucker representation, we just apply H-Tucker to the tensorial input space, and that is given a dimension tree and HT rank. The coefficient tensor assumed to follow H-Tucker format to obtain this H-Tucker regression model. And after a series of mathematical derivations, our model finally reached like this. And here L, small l, is just the level of tree. Big L is refers to the leaf level, and the TL is set of nodes having distance L to the root. So it's clear to see that from this formulation that the model can be fully parameterized just by the basis factors at leaf nodes and transfer metrics at the inner nodes. So it's clear to see the linear systematic part is only linear in each UT or BT separately, so we can alternatively update each one UT or BT at a time by fixing rex fixed. So given a collection of these samples and the parameter tensor can be estimated by solving the following estimation problem using MLE. So here L is the concave log likelihood, and B is assumed to follow H-Tucker format with a low run constraint. And so this is referred to by a block relaxation algorithm, which breaks the simultaneous estimation of parameters into a series low-dimensional parameter estimations. And they do this by recursively proceed the estimation of vectors by sweeping all the nodes along the dimension tree from bottom to the top in a sequential way. And for the convergence properties, it is shown that BRA can monotonically increase the log likelihood, and the estimation of parameter is guaranteed to converge if the likelihood is bounded. And it can also be shown that our BRA reached the stationary point wherever the likelihood stopped increasing. And in practice, we always expect our algorithm to converge to a local maximum. So therefore, we must run multiple times, including in order to increasing the chance of finding global optimal. So for the experiment, we test on the dataset, ADHD dataset, with brain images including 761 training data and 169 tested data. So as we said before, the predictor is MR. The response is binary outcome, and for the evaluation we experiment with different dimensions and ranks to see the classification error. How classification error can be affected with parameter size. And here you can see that our H-Tucker regression models significantly outperform the corresponding Tucker regression models in all the cases with less or few number of parameters. We can also see that for our non-regularized version of H-Tucker regression model has already comparable or better than the regularized version of the Tucker regression model. And and our second contribution is called Tensor-LGP. This work is published at IGASU 2015, and the target is, this work is focusing on the sequential nonlinear regression modelings and in the context of large tensor sequence. And this work was motivated by the fact that linear tensor regression is always based on the multilinear assumption is restricted because it cannot capture the nonlinearity between the tensor input and output. And the nonlinear tensor GP is able to flexibly model the nonlinear dependencies, but suffer from the high computational cost when the sequence of size is large. And so our Tensor-LGP takes advantage of the local online GP by assigning the tensor data points into a number of small-sized GP experts in an online fashion, then finding a few nearby local experts to make prediction with a Gaussian style. And so our Tensor-LGP can significantly reduce the cost for large tensor sequence. And it also, to our knowledge, we provide the first nonlinear tensor regression algorithm for the online setting. And So it's useful before introducing our work. It's useful to talk about the tensor GP. So GP is just a probabilistic model that can specify distribution over functions, such that the function value evaluated at a set of input points have a joint Gaussian distribution, and inference can be directly performed on the function space. And in the context of the tensor regression, Zhao adapt standard GP to the tensor valued input space, and by taking into account the multiple structure of tensor representation, leading to a tensor GP regression model at this. Now the set of observations are generated from a nonlinear function of a tensor, the order tensor. And so then the latent function can be modeled by the tensor GP prior, where the mean function is usually taken to be 0, and the covariance function with tensor arguments is predefined by a probabilistic tensor kernel. And for our contributions, we noticed that the high cost of the n cubic of GP training will restrict the applicability of the tensor GP to large scale tensor sequence, because the number of samples is usually required to be quite large to achieve a reliable result for the tensor regression tasks. So our tensor GP combined advantage of both tensor GP and the local GP, and it can be divided into two stages. First stage is called GP expert construction, and the second stage is called local prediction. And here is the framework, here is the algorithm, and when we have a new pair of new data tensor pair, x nu, y nu, and we just computed the similarity between x nu and the center of each local expert using a probabilistic kernel, and then we choose the nearest local expert whose center has largest similarity with the x nu, and if this similarity measure is greater than some predefined threshold, we just insert this tensor pair into that local expert T, and update the kernel metrics of that local expert accordingly. Otherwise, we just define this new tensor data as the center of the new local expert R+1, and initialize the kernel metrics. And in the second stage, after we partition the tensor data points into a number of small GP experts, we propose two searching strategies to make prediction. And the first strategy is called input-based searching strategy. Specifically, it find M local experts having highest similarity with the test point according to the probabilistic kernel, and then the response can be obtained by a weighted combination of these local experts. And the second strategy is called output-based searching strategy. It considers two steps. The first step is to find the nearest local expert CK to the test point in the X space. Then we find M local experts being to the output Y in the of this near local expert in the Y space as a candidate, and then we use the same weighting strategy to combine these local expert prediction. And for the experiment, we test our method on the ECOG data set to reconstruct the limb moments from monkey brain signals. So we use RMC and ALL as the evaluation metrics. For both RMSE and ALL, the lower value indicates the more accurate result. And unless RMSE doesn't penalize only inconsistency, and the ALL penalize both inconsistency and uncertainty. And here is the result for our method. You can see it's clear to see that both our tensor GP variants achieve the best result in terms of running time. The RMSE of our tensor GP is comparable to that of tensor GP, and for the ALL, our tensor GP is better than the tensor GP in this column. And although the tensor GP is slightly better in RMSE, the non-stationary in the signal make tensor GP with high uncertainty. So that's why our tensor GP, our tensor OLGP try to capture the lower structure to get a lower NLL by finding a few nearby local expert. And here is the here picture shows the learning time of our tensor OLGP grows only linearly in N with number of training samples, comparing to that the corresponding tensor GP grows polynomial in N cubic. And so our third contribution is called IHPRS. This work is published at IGASP 2016, and is focused on the sequential multilinear tensor regression and with both tensorial input and tensorial output in the context of infinite dynamic tensor streams. And in this context, we notice that although we can apply the batch method like NPRS, HOPRS to all the data each time a new data pair arrives, but they will quickly become computationally prohibitive for extreme large sequence. And it is also impossible to store all the data and or require them upfront. So for the sequential RMPRS, it's developed based on combining the recursive calculation scheme with the multiple representation of NPRS, but it still suffers from the slow convergence rate and low predictability. So in this case, our IHPRS is introduced to adapt the cutting-edge HOPRS to a setting of the infinite time-dependent tensor streams. And specifically, it recursively updates the projection matrix and cotensors over time by incrementally clustering the projected latent matrix in a latent space and by summarizing the previous data using only a few parameters. In this way, it can greatly reduce the sample complexity while remaining highly accurate result. And also, there's no need to store all the data. We just only need to store a few factors. And here is the framework. Oh, sorry. Before introducing our IHPRS algorithm, it's very useful to introduce what is high order PRS framework. So basically, HOPRS is used to, whose objective is to predict tensor output from tensor input through the extraction of a small number of common latent variables. And roughly speaking, give a pair of this tensor, and they decompose them jointly into a sum of Tucker blocks, such that such that the extracted latent variables have the largest covariance between them. And for the prediction, and we can notice that for the new response, and it can be predicted by in terms of loadings and cotensors like this form. And for our here's the framework. Here's our algorithm for our IHPRS, and we first reconstruct the internal tensor representation x tilde t minus 1 y tilde t minus 1 using a set of old parameters in order to summarize the previous old data and the current modeling state. And here, this latent matrix T represent all the clusters. Each row, there are n class number of row vectors. Each row vectors represent stands for a projected class center or projected new data point. And here is a codings and loadings and cotensor just can be viewed as a tensorial basis onto which the data points can be projected on. And now we have a set of a pair of new data. We can then concatenate the x new, y new to x tilde, y tilde along the first mode to get the augmented xy with a sample size of n class plus 1. And then we apply standard HOPRS to this data pair to extract a new set of parameters. And now we have all the parameters. We next allocated the projected new data represented by the extra row vectors to a set of class centers represented by the row vectors from 1 to n class. And how we do this, and we compute the similarity between this row vector and one of these class centers. If the higher the similarity between one of them and the extra row vector is greater than predefined value, and we just insert this extra row vector into that class center and update the that class center accordingly. And otherwise, we just define this new extra row vector as the new center of the center of a new cluster. And then we following the same pattern for the next time step. And here is the scheme, the whole scheme. And with all these parameters, we can make prediction at each step. And here is the experiment. We validate our method on the UNPM dataset to estimate the 3D human positions for video sequence. And we do this in online fashion, which means we first make prediction from the new data point and update the model using the new ground truth. And we use the RMSE and the Q index to evaluate the results. And the higher value the Q is, the more accurate result is. And here is the result. And this shows RMS, the error and CPU cost versus the elapsed frames for the total length of the video sequence. And we can see that our IHOPRS and RMPRS exhibit a constant trend, while the cost of CPU cost of HOPRS keep increasing over time. And we also see from this figure that our method achieves the best result in terms of the error. And our method, it's clear to see that our method is relative. The error of our method is relatively large at the beginning, but will quickly reduce to and remaining in a constant level as the test went on. And our fourth contribution is called kernel-based multi-block tensor PRS. It's published at the AAAI 2016. This work targeted on the batch nonlinear tensor regression modelings with multiple tensor input. And the motivation comes from the fact that single block KTPRS is always restricted in predictabilities because limited amount of information contained in the single predictors. And the multi-block MMSCR is a multilinear model that can handle all the predictor blocks in a hierarchical way, but still suffer from the low predictabilities. So we propose a kernel-based multi-block tensor PRS that to achieve this goal by extraction small number of the common and discriminant features, and followed by a regression step against these features. And our KMPRS can effectively integrate the information from multiple tensor blocks with different modalities, such unify the single and multi-block tensor regression into one general model. And we validate our work on to our knowledge, our work is first work that applies multi-block tensor regression to the multi-view human pose estimation problem in computer vision. And so here's the pic for the application. For example, here's a throwing action, snapshot of a throwing action taken from 4 multi-view cameras as well as 2 kinetic cameras. The question is, can the predictive performance be further improved by applying our method to the tensor data from either from multiple sources or from multiple modalities? And here is our framework. And without loss of generality, we considered 2 third-order tensor predictors and 1 third-order tensor response by concatenating all the observations along the first mode. And then we map our tensor data point into high-dimensional feature space using a nonlinear transformation. And then we perform Tucker decomposition simultaneously of phi1, phi2, and psi by taking into account common and latent features. And here, T common is just the common. T common represented the common latent matrices in the original dimension, and the common part captures the variation that present in all predictor blocks. Such describe all predictor blocks in what all predictor blocks have in common, and the discriminant T discrete 1, T discrete 2 is just represented the individual latent matrices associated with phi1 and phi2, and the individual part just explain the variation in their own individual block. And so by doing in this way, phi1, phi2 can simultaneously correlate with psi by having the largest covariance between these latent vectors in green, and phi1 can singly correlate with psi by having the largest covariance between the latent factors in red, and the same thing happened to the phi2 and psi. And for the prediction, for the new response, that can be jointly predicted by the 2 test point, and using this formulation, and we can see that here alpha is the hyperparameter vary from 0 to 1, indicated relative importance of each tensor predictors. And so rather than explicitly estimating the high-dimensional loadings or cotensors, we just need to find a few latent variables in the original space by a deflation strategy like this. In 2 steps, the first step is extract a common pair, T common, Q common from all the blocks, and the second step is to continue to extract the discriminant pair from deflated pair of phi1 and psi, and from deflated, and another pair T these two, U these two from deflated pair of phi2 and psi. And for the experiment, we demonstrate our method on the UMPM, and here is the Q index with a different. Here in the experiment setting, we choose 3 principal cameras, including left camera, right camera, and front camera, and we mainly focus on the 2 block situation. And here the Q index. Here the Q index performance, and we can see that our KMTPRS from here to here, significantly outperform the corresponding MMCR from here to here in almost all the cases for different settings. And we can also notice that there is a significant accuracy improvement for our 2 block situation comparing to the corresponding single block situation here. For example, for the table scenario in the blue color, the optimal Q index obtained by the left camera and the right camera, which is both are less than 0.6, which can be boosted to more than 0.68 by using our fusing strategies, showing the effectiveness of our method. And the 5th contribution is called recursive high-order HOPRS. This work will be published at ISHGAI this year, and is targeted on the sequential multilinear tensor regression modeling with both tensor input and tensor output for the context of large tensor sequence. And the motivation comes from the fact that it is very computationally expensive to decompose and compute the huge cross covariance tensor when using HOPRS for large sequence. And for the sequential IHOPRS of our method, we propose this method by incrementally by k-means clustering of the latent components to solve the large sample complexities. But computationally still remains a problem when the dimensionality complexity is large. And so we introduced the HOPRS by recursively updating the regression coefficient in a much smaller feature level instead of a large row observation level, by using a closed form solution, by integrating the low rank modification strategy of Tucker into PRS framework. So our work is very computationally cheap in both sample and dimensionality complexity, in both large sample and the dimensional complexity. And we validated our work on the challenging application of human post estimation and showing the great potentiality for the real fast prediction. And here's the framework. For the pair of initial data pair, we first perform simultaneous Tucker decomposition on them to extract a set of initial factors. And when a newly arrived mini batch of size B is cheaply decomposed into a set of incremental factors that contains variation corresponding only to the new data, and then we just append this set of incremental factors to the set of old factors to get a set of augmented factors. And after that, we just truncated these expanded factors into factors that lies in the space with original dimension. We do the resulting factors are found to maintain the principal components of the loading subspace, such to keep track of the changes patterns in the tensor basis. And finally, we updated the individual individual core tensors, which in conjunction with the loadings here to make the final prediction. And we repeat this procedure for the next time step, and we do the same thing for the all the steps. And here's the result. And we test this on the UMPM, and to show of frame size of 240 and with video sequence of frame size of 240 and 320, and we can see that our HOPRS significantly outperform both sequential IHOPRS and RMPRS in terms of accuracy and running time. And our method achieves highly comparable result with the batch HOPRS in accuracy, but extremely faster. And here is two figures showing the scalability of our RHPRS with increasing input loading size. And here you can see the right figure zooming in the lower region of the left figure, showing that our RHPRS is less sensitive to the increasing loading size compared to that of the HOPRS. And this reflects the fact that the impact of the large D-ranks on the computational complexity when using HOPRS has been significantly diminished by using our feature-based updating strategy. Okay, here is the conclusion, and we first view this from the perspective of the batch tensor regression models, and we first propose a linear H-Tucker regression, which can able to apply to a potentially very high order tensor, and we show this model is highly compact while being highly flexible, and is essentially useful for the brain data image analysis because of the number of samples is usually to be restricted. And the second batch method we propose is nonlinear KMT-PRS, and it is used for merging all the tensor predict blocks to predict, to get a boosted predictability by incorporating the kernel machines into the model and show that it's a generalized model that can unify the single and multi-block tensor regression into one framework. And to our knowledge, this is the first work of nonlinear multi-block tensor regression. It is also the first work to apply to the multi-block tensor regression to the multi-view human action motion estimation. And from the perspective of sequential tensor regression models, our first work is nonlinear tensor or LGP, which is by dynamically assigning data points into a number of small size GP experts. And we can show that it's computationally very efficient for the large scale data sets. And we also, to our knowledge, is also the first nonlinear tensor regression algorithm for the online setting. And the second sequential work is linear IHOPRS. And we do this by incrementally cluster strategy of latent component metrics. And in this way, it can greatly reduce the sample complexity to a low constant level. And it is very efficient in memory in that it only need to store a few number of factors. And for the linear RHPRS, which improves from the IHOPRS, that it can deal both large sample complexity and the dimensionality complexity. And it also shows the greater potentiality for the very fast real-time predictions on the human pulse estimation. And okay, here all my work. Thank you for your attention, and please ask questions.